Hello, everyone. Today, I'm going to talk to you about forces and free body diagrams. Okay, so we're first starting out looking at this body right here that's touching a surface and also suspended using a cable up to a ceiling. So if we look at these, if we look at this system here, we could say what forces are present right now. So certainly we're going to have a weight, and weight always acts down. So right now what I'm doing is my drawing on this picture that's given is just really my scrap. So I know weight is going to go down. What other forces are present? Well, certainly there's a normal, and the normal is perpendicular to the surface towards the body. So if the body in question is this cylinder right here, this surface right here is putting a normal up to it perpendicular. Okay. And I'm going to introduce something that you learned somewhat in geometry, and I'm going to phrase it in a way that I think is kind of clearer. Let me just make sure the focus is good. You notice here that there's 40 degrees between the surface and the horizontal axis. Geometry says that the angle between two lines is the same angle between lines that are perpendicular to both of them. So if we see the surface, perpendicular to the surface is where our normal is going to be. And this 40 degrees is between the surface and the horizontal axis. So that means that 40 degrees is going to be between the normal and the y-axis. Okay, and let's label that as normal. In addition, we have tension. And tension is always drawn away from the body in the direction of the cable or the wire or the rope. So in this case, again, if this is the body that I'm thinking about, this cylinder, my tension would be going up. And I'm going to label that tension. In addition, another force that's present is, let's assume that this isn't frictionless. The surface of the cylinder and the surface of the plane right here have friction between, and we'll just call it capital F sub S from sub F. And we know that this is drawn parallel to the surface, and it's opposite the direction of motion. So where I'm going to draw it, how am I going to draw it? Well, the friction, we could think about if this actually were to drop and this were to slide down, my frictional force would be right here, F sub S. Now let's call F for friction. Let's call it S. I don't want to talk about static and kinetic friction yet. So on this body, on this drawing for scrap, I drew the tension away along the direction of the cable. I drew the normal perpendicular to the surface and towards the body. I drew my weight down, and I drew the frictional force parallel to the surface away from the direction of force. Now, this is not a free body diagram. This is not a free body diagram. And the reason why is because everything is still connected. So I want to talk a little bit about internal versus external forces. So for instance, let's take that cylinder and let's connect it up to the ceiling. And right now, the body, the rope is pulling the body in this direction, but the body is also pulling the rope in this direction from the surface. Right now, these are internal forces, and they're utilizing Newton's law that says equal and opposite. So there's a tension here and a tension here. So when I just draw the body with the rope and the ceiling, the tension is inside here. It's an internal force. It's not until I take the body and separate it from the ceiling does tension become an external force. This is the same up here. I have my frictional force. This body is experiencing a frictional force going in this direction, but the body is also creating a frictional force that's equal and opposite going in the other direction. The important thing, which I do not think was conveyed in physics, because in physics they had to cover so many topics, they kind of went through this fast. When you have a free body diagram, you have to choose which body you want to analyze. And once you choose that body, you're going to remove it from where it is to make all those forces external. So in the end, I'm going to take the cylinder and I'm going to put its tension in, and the tension's at 50 degrees. I'm also going to put my weight in. Weight is always an external force. I'm going to put my normal going in. And my normal in this case, we found that the angle here is 40 degrees. And then I'm going to draw my frictional force. And this one is up at a 40-degree angle. Okay. This is a true free body diagram. You chose the body you want to analyze and you drew all the forces on that body. Now, what else needs to be on this diagram? We need to have a positive and XY axis. So I'm going to just draw it off to the side, but you could draw it on it if you want. Here's my X axis and here's my Y axis. And you could orient your X and Y axis any way you want. You could choose to orient it in a different angle, at a different angle rather. The important thing now for you to realize is that a free body diagram has to represent the body, the forces on the body once it's removed from all its parts. Because if it's not removed from all the other parts that it's touching, you're really looking at internal forces. Free body diagrams only represent the external forces. Okay? So what does a free body diagram need? A free body diagram has to have a positive X, positive Y, and positive Z if it's 3D axes, and it has it. We could draw it on the body or off the body. The other thing it needs to have is it needs to have the forces labeled, and they could either be labeled with their values or with a variable. And you have to show the direction. And in this case, in this example, the directions are showed with angles, but you are also familiar with having directions shown with distances. Okay, I'm going to stop here.